Hello, welcome everyone. So I've been asked to make a video about some skill you can learn and it can be useful for your scientific journey. So I've chosen the topic of Fourier transforms and we'll discuss that as we go. So I will share my screen. I'll have to flip my computer. So basically you won't be seeing me because I have to write on it to ensure that you understand. So, but my face has no value. What has value are Fourier transforms. So I'll share my screen, then I'll flip my computer, and then I'll start writing after sharing a PowerPoint. So I'm sharing the screen now, and here is the PowerPoint, and we can begin. So thank you all of you to attend this workshop, and I hope you have a great experience with all the lectures. So think you can see my screen, and I'll, as I said, minimize my window so that you can just see the what I'm trying to teach about rather than the empty ceiling because I have to flip the computer to write. Okay, good. So we are going to talk about Fourier transforms today. So let me choose a pen color. So Fourier transforms, the name comes from a scientist called Fourier who first came upon these things. So it's a long journey to reach this stage, but we'll build slowly. But why do we want to bother? Why are you spending your time in summer vacation to worry about this thing first in the first place? So, so let me start by saying that this is actually a great tool for studying functions. So this is a great tool for studying functions. Great, not tool, great tool to study functions. Okay, and then basically, so why we care about functions? So whenever I say the word function, some of you might be scared and you think only it's a physics or a math thing, why all scientists should worry about it. But this is not only physics and math, because everything you see around you, you see your eyes, they are taking some intensity of light and you have rods and cones which interpret them. You are hearing something that is actually a vibration in the air, which is going and hitting your eardrums, and you are hearing something, right? Whatever you are seeing on the screen is a bunch of pixels. It's a 2D function on your screen. Whatever you are listening is, again, an electrical signal being conveyed to you through your headphones or through your speakers. So this signal is being converted into from electromagnetic field to vibrations of some membrane, again, thanks to a magnet, and that's what is converting my voice, right? So it's not only math and physics, but actually all life, not only math and physics, but all of life, all life. This is true for functions. And I will show you an example where you can see that your heartbeat, which many of you know, if your parents or you went for an ECG, so then your heartbeat is a function. And then, if you invest or if or your parents are interested in investing, so then the stock market functions you see, they are also a function. So this one particular example, I will show you that how you can use the Fourier analysis to actually understand your heartbeat, and there are various other kinds of functions as well. But before we start on this big journey, let me tell you something which you already probably know. So what I'm going to tell you first is a simple thing called a vector, and we will establish an analogy so that you can follow. There will be some decent amount of math, but it will all be simple. Don't worry. There will be your friendly functions like sines and cosines. People get scared by trigonometry, but it's not very scary. They are very simple functions, well-behaved functions, and they only take value between 0 to 2 pi. How much harm can it do, right? So, but first I will give an analogy with a vector so that you understand. So imagine if you had to study vectors all your career just by looking at these kind of arrows. You have to add something, you take the head of the arrow to the tip of another vector, and then you add, right? So all your life, imagine if in all your career, if you had to just work with arrows, it will be extremely difficult, right? So what makes studying vectors easy is the fact that you can write any vector as v1i plus v2j, right? So if you can do that, then basically just ensuring that it's still recording. Yes, it is. Good. So So vector v is v1I plus v2j. And so these kind of operations make our life very, very simple. So it simplifies, all the vector operations. So as I said, you don't have to run around with the arrow and put its head to tail and all that. But basically, from this arrow, you can basically simplify addition. You can just add them like numbers and subtraction and so these kind of things you can easily do. And even more importantly, like dot products, so cross products, all these things you can do if you have this kind of I think I've moved to the next slide. So yeah, so coming back, so the dot product, cross product, everything can be simplified by the virtue of these this components and these bases, right? So what is component and what is basis? So let me indicate that. So here I and j, these vectors, which you know as unit vectors, they are called bases, okay? Or I will just call them basis vectors, okay? So these are the basis vectors, which we know what they are. So I vector is somewhere along this direction, j vector is somewhere along this direction. So there are two vectors, and by adding these two vectors in different magnitude, you can create any vector. For example, for our red vector here, its I component will be, 1, 2, 3, 4, let us say 4i. And then if we look at the y component, it will be 1, 2, 3. So it will be 3j. So this vector v is going to be red vector. Red vector, if we write this in terms of components, it's going to look like 3j plus 4i. So I'll write it like this, 4i plus 3j. Okay. So this makes a lot of operations easy. So you need basis vectors. And then what is V1 and V2? V1 and V2, they have a name. They are called components. So this V1 and V2, these guys, sorry, I'm overlapping my own writing. So I already apologize for any technical hiccups and my handwriting and all that. I'm not really used to teaching on screen. Otherwise, I would be a YouTuber. So I'm a teacher, so I actually teach on blackboards, which are big. And I don't do a lot of online classes. So V1 and V2, they are actually they are called components of the vector. So you need components and you need basis vectors to make your life easy, to make sure that you can do all these operations, right? So next thing, which is somewhat shocking, which I'm going to tell you, and so 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 up to this, you probably know, but what I'm going to tell you is somewhat surprising to you if you are seeing it for the first time, that functions can also be vectors. This is very, very surprising, right? How can functions be vectors? We know that, f of x is a scalar, and basically, how can a function be a vector? But if you look at a function, basically, it can be any kind of function. Then essentially, if this is x, this is f of x, then all these values you see, which are function values at different points, they can be considered as component of this function. So basically, f of x, you can write this as a vector, f of x0, f of x1, where these x0, x1 are these points, okay? Up to whatever value xn you want, right? So, but this xn can be infinity also. So functions are basically infinite dimensional vectors. So see, already in this workshop, you are learning about something which is very cool, which you can tell your friends about, that I have learned about infinite dimensional objects, infinite dimensional vectors. Okay, so this is very, very nice. Sorry, the slide keeps changing because the screen and I'm writing on it, so changes. Okay, so infinite dimensional vectors. But now, so as I said, to work with vectors, it will be easy if you can find some sort of basis, right? And what is particular about this basis, let me also write it down here, is that this is an orthonormal basis. So basically, these basis vectors, they are orthonormal. Now, what does this mean? So this orthogonal you might have heard of. Orthogonal means 90 degree. What does orthonormal mean? So by orthonormal, I mean that I dot j, this is 0, and this is same as j dot I. And then if you take I dot I, this is going to be equal to j dot j. and this is going to be equal to 1. So normal means 1, ortho means orthogonal, which you can see I and j here. They are basically 90 degrees to each other, right? So they are 90 degrees to each other. So that's why they are ortho, and they are normal because you multiply them with themselves and you get this 1. So if we have to write it in a more general form, another general way to write this is that we will say em dot en, where our ei's are basis vector. This is equal to delta mn. Now what is this delta? This is just a symbol which gives you 1 when m is equal to n. For example, in this case, I dot I, j dot j. So they are the same basis vector. So that's why you get 1. And this will give you 0 when m is not equal to n. For example, in this case, I dot j. So similarly, you can also think of ijk, and you can see that this thing will still apply to create an orthonormal basis. So when we have this functional space, it would be very, very nice if we can find some sort of basis which is orthonormal to write these functions into. And this is what actually Fourier transforms enables us to do. So what we are going to answer in this whole tutorial or session today is what is the orthonormal basis? So what is the orthonormal basis? This is what we are trying to find. And once we find it, you will see that it will be very nice for us to get a lot of information. We can do a lot of operations, and it leads to a whole different field. There are courses, full courses on Fourier transforms. In 30-minute session is not enough, but we'll try to see if we can get somewhere. Okay. So then let us just jump into it. So I have set the stage. I've told you how vectors are made easy by having bases, and I have told you that functions can be vectors. Now our job is to find, and as I said, we started with the promise of being able to study functions, which are very, very useful. So now we are going to see what kind of bases we can find for writing these functions. Good. So just to start with, as I said, we'll start with a particular case and then we will make it more general. And first of all, let me say that I'm going to talk about functions of time. Ideally speaking, it can be function of any variable. As I showed you, it can be a heartbeat, it can be stock market, it can be population, it can be visible signal and audible signal. But typically, just to make things easy, and that's how it's traditionally done in books. So if you look into a book, just so that you don't get confused, I'm going to talk about functions of time. So our functions f, they are going to be f of t. So this is what we are going to talk about. So, and before we jump into the more general function, first we are going to talk about periodic functions. So we are going to talk about periodic functions of time, and even then, I will take another special case, which will be even functions. So you'll see, oh, why are you taking such a specific case? I have so many functions which are not really what you're talking about. So we'll generalize all of them later. But we start with periodic functions, and in periodic functions, we are going to talk about even functions first, and you will see how it all comes together in a beautiful picture later. So even functions. Now, what are even functions? So even functions simply mean that they are symmetric about the origin. For example, if I have a function which looks like this, for example, so you see on this side of 0, the positive side, that is my pen. So trying to find a different colored pen. So which slide I was working with. Sorry for the technical glitch. Let me see. So I think I have just moved the slide. I have to go to a different slide. First, let me share the presentation, which is in full screen. Yes, this one. Yes. So yeah, here I was, periodic functions, which are even functions. And then let me pick color for my pen. Why am I not able to pick the color for my pen? Yeah, here it is. So yeah. Earlier I was able to do it with my pen. Now the only thing is that I'm not able to do it with my pen. I'm able to do it. I'm able to do it with my mouse, but not my pen. So that makes my job a little bit more difficult. But anyway, technical glitches. Without technical glitches, what is a tutorial session, right? So let me see again. Yeah. Okay. Okay. Whatever works. So even function. So let's come back here. So basically, in the function, you will see whatever is on this side, the same thing is repeated on the other side. So whatever is on this side, you will see that this is repeated on the other side. So the yellow side and the red side, they look the same. If you reflect, if you fold, for example, the sheet about this white line, then you will see that whatever you have on this side is the same on the other side. Okay, so good. So these are even functions. If we have to write them, we'll say f of t equals to f of minus t. And then basically, so these are called even functions. We'll just write some subscript e, and let us see how we can analyze this function, and then we will move to more general things from here. So, and as I said, we are going to look at a periodic function. I by chance drew a periodic function already, but let me just draw it more nicely. So for a periodic function, let us assume that it looks something like it can be any funny shape. It need not be nice. It can be something like this, and basically continues. So there are three things. So I should make three things. Yeah. So this kind of function, right? So a periodic function, which is even, and we want to study how to represent this kind of function. So one thing you will notice, if it's a periodic function, then it must have a period. For example, here, we take the middle point of this to the middle point of this. So if this is 0, then this has to be time period t. Or you can also take the period to be minus t by 2 to t by 2. So for example, you can take this as minus t by 2 and this point as t by 2. So this interval is also t, and this interval is also t. So we are talking about one period, because if you know the function in one period, then basically you know it in all other periods. Okay, good. And this period is also recognized by some characteristic frequency, which we call omega naught, which is 2 pi by t. So this is the frequency of the function, which means how often it repeats. Frequency means how often it repeats. Okay, so now I'm going to give you a theorem. I won't give a full proof, but basically you can try to prove it yourself as part of assignment. But I'll give you some intuition on how this works. This is a theorem. So theorem, and this is the thing which we were looking for. So as I said, we are looking for orthogonal functions here, but rather than letting you move in the dark, I'll actually directly give you the answer. That if you integrate over one period, so this can be minus t by 2 to plus t by 2 or 0 to t. So let us take 0 to t. We can choose this period based on our convenience. So what I'm trying to tell you is that if you take cosine of m omega naught t, and cosine function, I guess all of you know. So if you have one cosine function with one period and cosine function with another period, and you integrate this, then basically what you are going to get, I tell you, is going to be t by 2. And then what was the condition for orthonormality, which is delta mn, which means that when m is equal to n, you will get t by 2. When m is not equal to n, you will get 0. And here, by the way, in this case, we are saying both m is not equal to 0 and n is not equal to 0. Because when both are 0, then we know what this integral is. So we'll not prove this, but I'm just letting you know that we can break this into different cases. So case 1, when both m equal to n equal to 0. So if you integrate this 0 to t, and you know that cosine of 0 is 1. So this will be just 1 dt. So in this case, it gives t. So this is the only exceptional case. But in other cases, as I said, you can prove this. And I'll give you maybe one general idea of how to solve this. So let me just choose a different color so that you can appreciate. Yeah. So if this is our integral, so this integral, if you know cosine identities, cosine of a, cosine of b can be written as half cosine of a plus b. So it will be m plus n omega naught t, and then plus cosine of m minus n omega naught t. Okay, so this is what it's going to look like. And then, so what is this m plus n omega naught t? So omega naught is the frequency when you are completing one cycle in time period t. If you have some integer z times omega naught, then basically it is going to be 2 pi by t by z, right? So the time period has become, so if z is 2, time period has become half. If z is 3, time period has become 1/3. So it will complete. So whatever z is there, so this means z cycles in z cycles in t, z cycles in time period t. So in one time period, if you have some m plus n omega naught, this means m plus n cycles, and this means m minus n cycles. And it will be complete cycles. So I should say complete cycles, complete. And why this matters is because cosine and sine, they go both positive and negative. So if you're completing integer number of cycles, this is going to give you 0. So if you're going to integrate over something which goes positive for the same amount of time and negative for the same amount of time, then this integral dt is going to be 0. Slide changed. So to go back to the previous slide. Yeah. So integral dt is going to give you 0 if m is not equal to n. Okay. But when m is equal to n, then basically something interesting happens. So I think my meeting controls are being shown here. It's hard for me to write, but I'll make a box and try to write it here. So when m equals to n, basically the first one will be 2m, so it will still give you 0. But the second one will be interesting. So you will get half. This integral will still give you 0 plus 1 here, because m equal to n means m minus n is 0. This dt, so that's why you get t by 2. So again, I'm going to leave this as an exercise for you. So I'm just giving you a basic hint of how to solve. Basically, you can see you get half, and when you integrate from 0 to t dt, 0 to t dt, then basically you will get t by 2. That is why we say that this is t by 2 delta mn. When m is equal to n, this cosine 0 gives you t by 2. When m is not equal to n, both of these things are integer, they complete full cycles. So you get plus and minus equal, and that's why you get a 0. But this is part of assignment for you to prove. Okay, good. So once we have this, immediately you should go back to your vector example, and you said, Rahul, I have figured out an orthonormal basis for our functional space. So I dot j, for example, was 0, I dot I is 1. But now we have figured out that the different in the functional space, some functions which are going to be orthonormal. Okay, good. So now, right. So we have figured out. So now, how can we use these orthogonal functions to find the components, right? Because remember, when we were writing the vector, let me change my pen again. When we were writing the vectors, this f of t, sorry, f of t is a function. So we are talking about vectors. So this v was v1i plus v2j, right? So to be able to write these things, what we needed are these components, right? And I and j, which are the basis. So basis we have found. So half job is done. So basis we have figured out. They can be our cosine of m omega naught t, right? How do we find components? So this is why I was saying that this vector analogy is very, very good, because now you can, this is our problem. This is what we are going to solve. So half the battle is won. We have found some orthogonal basis. So basis, and in fact, it is orthonormal also. So we have half the battle is won. We have found an orthonormal basis for functions. Now the remaining half of the battle is finding the components. So for this component, you can see that we can write v1 as v dot I. Okay. So if we take the dot product of a vector with any orthonormal basis, then basically this is going to be giving us the component. Why? Because if we write this as v1 I cap plus v2 j cap, and then we take dot product with I, then we know that I dot j will give you 0, and only I dot I is going to give you 1. So this is why it gives you 1, because the other thing is going to give you 0. So this is why orthonormal bases are very, very useful, and they can give you the components. Okay, good. So now let us write that for the functional space. So for the function, so if we write this integral I, I'll tell you what this integral I is in a bit, because you can solve it. if I write this as some function fe of t, and I integrate with cos n omega naught t, so I'm just doing this kind of thing. So I have my vector, which is the function, and then I'm doing cos n omega naught t, which is my basis. And if I integrate over dt, then basically what we see is that, so what should we get? So we are assuming that our this function, this is a vector. So this vector is in this basis. So this vector should look like a0 cos 0t plus a1 cos 1t plus a2 cos 1 omega naught, I should say, 1 omega naught t cos 2 omega naught t plus dot 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 dot, right? So because that's how we write vectors. We write vectors as some component. So there will be some an cos n omega naught t plus dot dot dot. Okay. Now, what is interesting here is that we know that if this is n, then this will only give me 1 when the other thing is n. And all these will go to 0, like it was happening here. I gave me only I. Okay. I gave me only I, and rest of them all are going to 0. So what is this going to be equal to? So this an you will get. So this will be an, and then cos n omega naught t cos n omega naught t. So m equal to n case, which we solved for last time. So what you are going to get is t by 2. Okay. So then if we have to write what is our an for any general n, this is going to be 2 by t integral over one time period. So this is over one time period. It can be minus t by 2 to plus t by 2 or 0 to t or any period you want. Fe of t cosine n omega naught t. Beautiful. And then a0, as I said, that's a separate case. So a0 we know gives us only t. So this is going to be only 1 by t rather than 2 by t. And again, integral over t, f of t. Why this is not 2 by t, 1 by t? Because if you go to the some time back, I have showed you that when m equal to n equal to 0, then we can integrate that easily. And that integration gives us t rather than t by 2. That is why we get 1 by t, this, and then cosine 0 is going to be 1. So we don't write this. So this and dt. What is interesting is that this component, if you look at it, if you have studied integrals, this is actually average value. So, or we also call it DC value of the Fourier transform. And then this an. So still so what we are talking about is a Fourier series, not transform. We'll build up to transform. And we have found ans. Okay. So what was our initial goal? To understand the functions, right? So basically, let me write this function for you. So, so this function fe of t, I'm proposing that this is an even function, can be written as a naught plus a1 cos plus sum over all these things. So basically a1 cos omega naught t plus a2 cos 2 omega naught t plus dot dot dot, which can be generally written as a naught plus sum over n equals 1 to infinity cosine of n omega naught t an. Now what you need are these components. These are the bases. So these components I've already told you is that my a naught is going to be 1 by t integral over one period, my function, and then these ans are going to be 2 by t integral over time period, my function, even function, times cosine of n omega naught t gt. Okay, this is very good. So now we can write our functions in terms of these waves. Now, why is this useful? Let me just, I have promised you I'll show you a heartbeat. So let me show you a heartbeat. So there should be my browser open somewhere. Can't really see it. Nevertheless, let me see. This is something else I was working on. Interesting. Can't see the, anyway, so yeah, so first of all, I take no credit for this. This is lpsaswarthmore.edu. You can all go to this website and check out. They have very nice articles and very well explained things about Fourier transform. What I wanted to show you here was very quickly this. Okay, so I just told you that any function can be written in terms of these cosine waves. Okay, Okay, I only said even function. So let me actually complete this picture, then I will come back to this. So yeah, so this is only about even functions, right? What about odd functions? Okay, and what about general functions? So this I'm going to state without any proof because everything goes like the same, which I did earlier. So we know that cosine functions are even functions. And if I have to write odd functions now, fe of t, then basically this, sorry, fo of t, then without proof, I'm just going to tell you that this is going to be sum over n equal 1 to infinity, some bn, some other coefficients, and then rather than cosine, you can use sine functions. This is the cool part, okay? So cosine functions we all know are even functions and sine functions are odd functions. So you can make a linear combination of sine functions. So since this is odd, this will give you odd functions, okay? So it has become difficult to change my color. Otherwise, I would be changing it all the time. So, okay. So this is odd. That's why it gives you an odd function. And this is even. That's why it gives you an even function. Okay. So, so this I'm stating without proof, but the proof will follow similarly that if you have an odd function, you can write it in terms of this kind of function. Now, what if you have to write a general function? Okay. So if you have to write a general function, then basically what you can do. So again, this is also I'm something stating without proof, and proof you can try in the assignments, that any general function f of t can always be written in terms of an even function of t plus an odd function of t. So this is true for any general function. So in our case, we are only talking periodic function. So any general periodic function, but this is true for any function. Okay. So, so basically, how you do that is that you say my f even of t is going to be half f t plus f of minus t. Then you say my odd function, I define it to be odd of t half f t minus f of minus t. Now, I'm not going to prove it. That's again a part of assignment that you can show that indeed this is odd, indeed this is even. And here you can clearly see if you do fe plus fo, this f of minus t is going to get cancelled. And what you will get is half ft plus half ft, which is going to be ft. Okay. So for any general function, you can write this in terms of these cosine waves, and how you can write this is you say a naught. So again, I will again tell you that right now we are still talking about periodic function. The period can be very, very funny, but we are still talking about periodic function. When we go from periodic to aperiodic, any general function, then the series becomes a transform. So this is what we are trying to build towards. But for now, for any periodic function ft, which can be a general function, we can write it as sum of something like this, n equals 1 to infinity. And we know that for the even part, we get cosine terms. So an cos and omega naught t. And then for odd terms, we can get sine terms, sine and omega naught t. So when you combine both odd and even, you can write any general periodic function in terms of cosine and sine. So, and again, if I look at the these coefficients, I've already told you a naught is going to be just simply the average value or the DC component. An, I have told you, an is 2 by t, integral over a period. These are all integral over a period. F of t, cosine of n omega naught t dt. And then bn, again, I have not told you, but all the logic follows exactly the same. So bn is going to be simply 2 by t, integral over a period, f of t, sine, t looks too big now, so we'll just say sine of n omega naught t dt. Okay, so this is how you can express any kind of periodic function using simply cosines and sines. And now let me go back to what I was promised you in the beginning of the session, that I can show that your heart beats with these kind of things. Okay, so yeah, so you see there here what I'm showing you here. Again, it's not from me. This is from LPSA swarthmore.edu, and you can see that here essentially this is an electrocardiogram. It's also called an ECG. And basically, if you just add the average, which is the DC term plus first harmonic, it looks like this. The red line, you can see that this red line is not a good approximation to the blue line, right? Blue line is your ECG, electrocardiogram. and the red line is just first harmonic, which means cosine omega naught plus sine omega naught. It cannot do a very good job. Now you add one more, okay? So, okay, it has taken some sort of variations, but still not very good. Now you go higher, you go up to fourth harmonic. So up to fourth harmonic, you can already see that, okay, it's able to reproduce my peaks very well. So what are these harmonics? These harmonics are simply multiples of omega naught. So now we have terms up to cosine omega naught, sine omega naught, cosine 2 omega naught, sine 2 omega naught, cosine 3 omega naught, sine 3 omega naught, and cosine 4 omega naught, sine 4 omega naught. But if we go up to 10th, you see already very well approximated. And if we go up to 20, if we take 20 sines and cosines, and sines and cosines are not very difficult function, you can see we have a very, very good approximation of this ECG pattern using simply sines and cosines. Okay. So this is how you can write any functions in terms of sine and cosine. Okay. Now you'll be like, okay, what is the use? You know, I wrote a function in terms of sines and cosines. Why should I care? And why is it of any use to me? Right. You have just increased my complication. Okay, but let me give you an example here, which is actually, I don't know if it's below. Yeah, it's here. So yeah, so you can go to this website and check out this example. Here a person is saying hello. So you may not be able to hear it, but you can go on your own and try to see what this person is saying. So if you take the Fourier transform, so again, I'll tell you what transform is, but if you write a frequency representation, it tells you what waves are present. This much. So if this number is high, which means that there is higher magnitude of this frequency, which means this omega naught, then lower magnitude of this frequency, which is about 300. Then, so basically what a Fourier series is telling you is what kind of waves are present in your overall signal. Okay. And so this is with respect to times. If you saw hello, how does the amplitude looks? So this is the amplitude, you see, this is the amplitude, and this is as a function of time. And if you take a Fourier transform, then this looks like this in the frequency space. Now, if we add noise to it, okay, let us say it's a noisy environment. Let's say you are recording a video on an aeroplane passes by, or something happens, and then basically your time, if you look at the time signal, it will look like this. Now, if you look at this time signal and this time signal, they both look very, very identical. I mean, okay, not identical, but it will be very hard for you to figure out how to remove this noise and how to get from this to this. Okay. But when you take a Fourier transform, or you write it as a Fourier series, you can very clearly see that, okay, I have two very high frequency noise, two very high peaks in my frequencies. So there is a wave at about 300 and there is a wave at about 700, which has added on to my signal. So you can easily identify, you can easily remove them, you can easily manipulate them. So this is why the Fourier analysis is very, very useful, because it can help you untangle the kind of waves which are present. And as we know in physics and mathematics and all sciences, we model a lot of things with waves. So if we can break something down in waves, like vectors, you break it into components, you can manipulate these components. You can make one component 0, you can make one component big, you can make one component small. And this is what Fourier transform allows you to do. Okay. So this is why this is very, very powerful formalism. And right. So we have talked about periodic functions and how to write periodic functions in totality, right? Now, the only last step is remaining, which I will do here, and I will leave the rest to you. So the last step is actually writing this in a more simpler fashion. So if you know complex numbers, I square root -1. If you know complex numbers, you can write this thing even more beautifully. So we know that cosine theta. So in complex numbers, there is something called Euler's formula, which is very, very useful. So this tells us that e to the I theta is cosine theta plus I times sine theta. By the way, I was told that the time is about 30 minutes. I think I've taken 40 minutes. So if you want to stop, this is a good time to stop. And the rest of the video can be either edited by the team or it's not required. And they can edit slightly before also, I think, just when I was showing the example, because that completes one part. I'm just making it more beautiful right now. So this is the Euler's formula. This is I. If you know complex numbers, then you can write the previous expression, which was only in sine and cosine, much more beautifully. The way we do it is we realize that cosine of theta, if you follow this formula, then it's e to the I theta plus e to the minus I theta divided by 2. And then sine theta, it's e to the I theta minus e to the minus I theta divided by 2 times I, because it's in I now, so you have to divide by I. So this is in complex numbers now. Now, if you, so what we had earlier, if you look here, then basically we only had these n's to be positive, right? So we only had positive things. But here, if you see, if I allow my n to be negative also and go to both positive and negative numbers, then I can use these complex numbers rather than writing cosine theta and sine theta. And as you will grow up, you will realize that working with exponentials is much, much better than working with trigonometry, because trigonometric formula you don't always remember, right? But with the exponentials, the products and everything else becomes very, very easy. So in this case, again, the proof is left to you as assignment. But what you can write your function, which I wrote earlier, n equals minus infinity to infinity, Cn e to the power I n omega naught t. Now, this is often called as a synthesis function, which means that you are synthesizing the function. So this is called synthesis equation for Fourier transform. And so here you notice that my n's are also going negative. Now, what is the relationship of this Cn with my earlier a and b? So that I will write down for you, and it remains for you to be proved that a0 is going to be c0. That is going to be okay. And my Cn's are going to be an minus I bn by 2. Okay. And basically, so if I just have to write an and bn, you can show that an is 2 times real part of Cn, and bn's are 2 times minus 2 times imaginary part of Cn. So Cn has become a complex number, but for a real signal, for real f of t, for real numbers, Cn is going to be C of minus n star. Okay. So this relationship will hold for complex numbers. Okay. So this is very, very beautiful. And so I've given you a synthesis equation. And so there is also something called analysis equation. Analysis equation is simply the formula you will write in terms of these. So these things. So here, this was synthesis. And these are analysis. I'm not going to repeat it here because you already know how to write A and B. So you can write C also. Okay. Okay. Now, so we can write any general periodic function in terms of these exponentials. Now, I'm just taking the last step. What about the aperiodic function? This is only the last step. After this, I'm done. So aperiodic functions. Right. So for aperiodic functions, basically aperiodic functions, it's a very neat trick people do in mathematics. They would say that any aperiodic function you have, and anything, they will say that it doesn't repeat. Okay. So aperiodic means doesn't repeat. But mathematicians are clever. They would say that it repeats at infinity. So this is very, very interesting. Basically, what this means, I'll put a solution one. So what this means is that this t is going to tend to infinity. So if you take this time period capital T tending to infinity, then basically you should be able to do aperiodic functions also. So we have already done any general kind of periodic function, then you can do any general type of aperiodic function. Okay, good. So let us see what this limit actually leads to. Okay, so we had f of t, which we were writing sum as n equals minus infinity to infinity Cn e to the power minus I n omega naught t, right? So what we will do, we will write this omega naught explicitly as 2 pi over capital T, because our limit is on t. Or another way to do it is basically we will leave it as omega naught, and we will realize that if t is going to infinity, my 2 pi by t is going to 0. Okay. So this omega naught is going to 0. Okay. And so what we will do is we'll multiply this by 2 pi by t and divide this by 2 pi by t. So I'll get t by 2 pi here. Okay. So this will be 1 by 2 pi, summation over n going from minus infinity to infinity. Then we have some t times Cn, and then e to the power minus n omega naught t. And then there is a very small number here. So rather than calling it omega naught, basically, if t becomes very, very big, what this is telling you is that omega naught has become small. So this is actually a small number, okay? And you are taking multiples of this small number. So basically, how is this going to look? So n omega naught is going to be omega naught, omega naught, omega naught, omega naught, 3 omega naught, 4 omega naught, 5 omega naught, 6 omega naught, 7 omega naught, 8 omega naught, 9 omega naught. Okay. So basically this, if the distance between them goes to 0, then this becomes a continuous variable rather than a discrete variable. Okay. So this sum, which was discrete earlier, if you make the spacings very, very small, then this sum is going to convert into an integral. This is what is definition of Riemann sum also. And this 2 pi by t is some delta omega, okay, or omega naught, but I'm just writing it as delta omega, just to make it more similar to what we are already familiar with, which is Riemann sums, if you have done any calculus. So if my delta omega has become small, okay, then this whole thing can actually be written as an integral. So this will be 1 over 2 pi integral minus infinity to infinity. And then this TCN, so these are coefficients, right? They were as a function of each n. But now n omega naught, n times delta omega has become a continuous variable. Let's call this variable omega. So now these coefficients have become continuous variables. So this TCN, we will call some f of omega, capital F. And then e to the power minus I omega t, and then this thing is d omega. Okay, so these two things we will write. Okay, very good. Now, so this is the synthesis equation now. So you can see we have written any general function in terms of, so this is the synthesis equation now, or this is also called what I'll tell you later is inverse Fourier transform. Inverse Fourier transform. So what is the direct Fourier transform? I'll tell you. So this is inverse Fourier transform. Any function you can write in terms of some components which are multiplied by a plane wave e to the minus I omega t, which is cos omega t plus sin omega t, integrated over d omega. Now the last step is, what are these f of omega now? What are these f of omega? So f of omega, we know that f of omega we had seen earlier. So yeah, so we know that our CNs, they were, so did I write this earlier? If I did not, I should have written. Yeah, oh, I said it's a between A and B, and so I didn't write it explicitly, but yeah, so I should write CNs here are given by 1 over T because there is 2 times, right? So T by 2, it will be removed. So you get 1 over T, and then integration 1 over T integral over f of T e to the power minus I and omega naught t. So this is the synthesis equation. This is the analysis equation, where we are finding these coefficients, these vector coefficients. Okay, I told you vectors, components. These are the components. This synthesis equation, this is the analysis equation. And so this is what we'll use. So basically, we know that CNs are 1 over T, integral over T, synthesis equation. This is the analysis equation. So this is f of T. See, have I written it correctly? Yeah, integral this and then dt. So e to the power minus I omega t dt. And as I told you that this time period can be minus t by 2 to plus t by 2. So if I write minus t by 2 to plus t by 2, I take t on this side. So tcn equals integral minus t by 2 to plus t by 2 f of t e to the power minus I omega t dt. And this TCN, then basically, as we take the limit t going to infinity, as I said, t becomes very, very big. These coefficients become continuous. So we get f of omega, which is equal to, this will be minus infinity to infinity, f of t e to the power minus I omega t dt. So this is what is called as Fourier transform. Okay. So this is what is called as Fourier transform. Okay. And so this is the analysis equation. Earlier we used to call this analysis equation, or let me, rather than writing it here, let me write it this. So this is analysis equation. This has become our Fourier transform, and the synthesis equation has become the inverse Fourier transform. Okay. So rather than again writing in the continuous part, I will say this is inverse Fourier transform, and the synthesis part was here, what we had. So this was synthesis equation. It is converted into inverse Fourier transform. So now for any function, you can actually use these kind of techniques to figure out what component of wave is present with what magnitude, and you can manipulate these magnitudes to play with your function. And after manipulating, if you want the original function back, you go and calculate this guy and you get the original function back. So this is what you can do. And I was asked to provide assignments. So these assignments can be, there are multiple assignments. So assignments, you can show, first of all, that integral of cosine m omega naught t times cosine of n omega naught t. This is equal to delta mn times t by 2, where the integral is some 0 to t, where t is some period. Omega naught is 2 pi by t. This is integral dt. So this is something you can show for m not equal to 0, n not equal to 0. Okay. You can show the same thing for sine. So show the same thing for sine. That's trivial, so I won't ask. And then the other thing you can do is establish the relationship for the coefficients Cn. Okay. So and other thing you can do is show that ft, as I said, can be written as fo of t plus fe of t. And you can show that this f of o of t is actually an odd function. Fe of t is actually an even function. So that's something you can also show in your homework. Prove that fo of t is indeed an odd function, and show that f even of t, which is given as half ft plus f of minus t. Yeah, I think I can't write too much towards the right. F of minus t. Oops. Okay. Let me write it down. So this is odd, and then fe of t half f of t plus f of minus t. This is even. This you can also show. So this is 1, this is 2. And then the third part, show the values of Cn. Okay, so show that Cn is actually An. I think I wrote half times An minus Bn by 2. So basically, where are Cn values? Cn values. Yeah, so An minus Ibn by 2. I think there should be a half in An also. Let me double check. Yeah, this An also needs to half. Okay, good. So you show me that this is An by 2 minus Ibn by 2, and show that C0 is equal to A0. Okay. So these are the exercises you can do, and that will ensure that you understand this Fourier transform carefully. Okay. With that, I will take your leave, and thank you again. Stop screen sharing, and goodbye.